Okay, welcome back, everyone. Hope you all had a good weekend. I'm going to continue today talking about minimum spanning trees, and in fact, I think minimum spanning trees will pretty much take us through to the end of the week and the end of the course. Um, so today we'll finish discussing two-dimensional and more generally Euclidean minimum spanning trees, and start discussing the mean field setting. Then my plan for the rest of the week is to first talk about the global structure of the minimum spanning tree of complete graphs. So in the mean field setting, similar to what we did for uniform spanning trees at the start of the course. So we'll try to get a handle on global distances. We won't get quite as detailed for the minimum spanning tree. I won't talk about precise details of finite dimensional distributions, just about the diameter, the typical distances between points and the extreme distances between points. Then we'll focus on the local structure. Oh, there's a fair amount of noise coming from somewhere. I think I'm going to mute someone. Then we'll focus on the local structure of minimum spanning trees and use the local weak convergence methodology that was alluded to and used in Kavita Ramanan's lectures to describe in a bit more detail the local structure of the mean field MST, and finally use the local perspective to understand the typical weight of the minimum weight spanning tree, which after all is quite a natural parameter to study, given that the tree is defined by minimizing the weight. Okay, so that's where we're headed. As I said, today we're going to be starting off by finishing our discussion on the Euclidean setting. You all should be able to unmute yourselves to ask questions, and I'll keep an eye on the chat as well. So let me remind you where we left off on Friday. So we saw two connections between so minimum spanning forests and critical percolation. Right. So so the first of those said that if the probability that the origin is in the cluster invaded by invasion percolation or a Prim's algorithm, starting from a far off vertex V, so if that probability tends to 0 as the distance of that vertex from the origin tends to infinity, then on the corresponding lattice, the probability of percolation at the critical parameter PC is equal to 0. Okay, so perhaps I should say that the whole thing is happening in ZD there. So that we proved rigorously, and I think someone remarked that in fact the proof goes through on any so fully symmetric transitive graph, so a graph where there's an automorphism sending any vertex to any other vertex that has the property of unique infinite clusters, which we discussed in that lecture. So the proof is somewhat more general than how I presented it. And then we also saw this this picture of invasion percolation, which was a little bit more heuristic. As sort of zooming in on the critical percolation parameter by exploring this sort of sequence of pawns, a sort of first collection of vertices, which it builds a spanning tree for, and then some edge, which is sort of the largest weight edge that it will ever explore, followed by another second pond, a second sort of spanning tree of some region, and then the largest weight edge that it will ever explore after that. And sort of continuing in this way, that this sequence of sort of future maximal edge weights get closer and closer to the critical probability. And we, in particular, stated that, you know, if so, En are the edges explored by invasion percolation on ZD from an arbitrary starting point. The symmetry means we don't, it doesn't matter where we specify, where we start from for the statement to hold, then the lim sup as n tends to infinity of the edge weight of En converges almost surely to the critical probability PC of ZD. Okay. And I'd like to maybe use this. Well, no, I think I'll leave the discussion there, and now just unless there are questions, focus in on the case of 2 dimensions, which is a setting where a little more can be said using the special structure of planar percolation. Okay, so now we'll focus on 2 dimensions, and in this setting, there's the famous Harris-Keston theorem, which identifies the percolation critical probability as a half, and also says that there's no percolation at criticality. So if you look at the probability at a half of an infinite cluster existing, that probability is 0, right? So equivalently, this is saying that this statement is saying that if on, you know, this lattice I've got drawn right here, you just flip a fair coin to determine whether each edge is going to be present or absent, right? And color the present edges blue and the absent edges pink, then the probability that there's an infinite connected cluster of blue edges is 0. Okay, but because the coin is fair in this case, because the critical probability is exactly a half, that also means that the probability of an infinite cluster of pink edges is 0. It doesn't matter in this special case whether I talk about the sort of edges we add or the edges that we don't add, because the 2 marginals have the same, or the 2 subgraphs have the same distribution. Okay, that wouldn't be true in dimensions 3 or higher, where the critical probability is less than a half. There, you know, if you look at the absent edges, they'll be more denser than the present edges at the critical probability, and so the sort of, if you reverse the role of red and blue, you don't see the same picture. Okay, so a sort of important consequence of this for the story about minimum spanning forests and trees is that it means that you know, a fixed point of the lattice can be sort of separated from infinity by large closed or open circuits. So I'm using the term closed and open to refer to that's sort of equivalent language to saying edges that are absent or present. Open edges are present and closed edges are absent. Okay, so so let me make a definition. So if we're given a subgraph G of Z2, then an open circuit around, well, let me say, let me start again. I want that I'm making things a little more complicated than I need to. So we'll say that a closed circuit around 0 in Z2 P. So this will be a a circuit, all of whose edges have weight greater than P. Right, so remember that we defined this graph here as having edges. So the set was the edges E for which the weight was at most P, right? So so these are the open edges, and then we're just saying a closed circuit is a circuit all of whose edges are closed. So that's a picture like this. Right? And maybe, I think I just said that I was going to use pink for closed edges. So it's a picture like this. Okay. And the fact that at P equals a half, the probability of percolation is 0 means that we can find arbitrarily large closed circuits encircling the origin. So for any integer n, almost surely, so the critical percolated lattice has a closed circuit around 0, which does not intersect the centered box of side length 2n around 0 either. So not intersecting minus n squared. Okay, so this is just saying, you know, no matter how far away from the origin you go, then you can still find with probability 1 some barrier, some closed circuit which witnesses the fact that the origin is not an infinite component. And the reason that this is implied by no percolation is just that you know, if there was some chance that there was no such closed circuit around a large box, well, that would mean that there had to be an infinite path starting from the boundary of that large box. Okay, but then if there were an infinite path starting from the boundary of some large box, then with positive probability, you could get really lucky and just have, you know, all of the edges in this box come up heads. They're all open, and that would create a path from the origin to infinity. Okay, so if there were any chance of this event, any positive chance of this event failing, that would also imply a positive chance that the origin was connected to an infinite component. Okay, but you know, now using the special property that PC is a half, this also means that there are open circuits around 0 of arbitrarily large size. So equivalently, that's since PC is a half, almost surely, so Z2 a half has an open circuit. Around 0, which doesn't touch a large box. Okay, so that's sort of the only facts from percolation. I'm not going to prove that, but it's one of the sort of fundamental facts about planar probability. You can find it in presented nicely in many textbooks, including so the percolation textbooks by Grimmett or by Bolobash Riordan. If you're looking for a reference, those are 2 reasonable ones. Probably it also appears in Hugo Duminil-Copin's notes from this very sequence of summer schools a couple of years ago. I can't swear to that, but I suspect it's in there. Okay, but now I'd like to, you know, use this fact to say something about minimum spanning forests. So this goes back to Chase and Newman again. I think I stated this on Friday. So so in Z2, almost surely the minimum spanning forest is a tree. Okay, And I've dropped the use of wired or free because we said they were equivalent in this setting. But I'm just going to make a quick comment about those terms, which I didn't make last lecture. After the lecture, someone kindly pointed out to me it would have been good to sort of explain where the terms wired and free come from. So one way you can, rather than sort of defining these objects directly in the infinite volume limit, that you could sort of try to understand what the minimum spanning tree of Z2 should look like, is precisely by, taking a large box, okay, with minus n squared like we've been using here, taking the minimum spanning tree of that, asking what the local structure is near the origin, and hoping that those local statistics converge as n tends to infinity. So you just look at a small window of size k, a small box of fixed finite side length 2k, and then let n tend to infinity, and hope that the sort of local picture in here converges for any k as n tends to infinity. Okay, but then there's sort of two things. There's some question about what you do at the edge of this large box. Do you, leave all of the? Do you just view these as kind of independent points, so that each one has to be attached to separately, or do you wire them all up? Do you join them by a circuit to start, so that then you have sort of trees coming in from an outer circuit, and then the question is, a natural question is, does the picture you get depend on your choice of boundary conditions? So wired boundary conditions, where you make an outer circuit, you can show yield the wired spanning forest we discussed, and free boundary conditions, where you leave the boundary vertices completely disconnected, yield the free spanning forest. Okay, and in the theorem, that they're the same in, and of course that makes sense not just on ZD, but on more general graphs. You can take an exhaustion of your graph and look at the local structure and hope that converges. Okay, so it turns out that at least in the Euclidean setting, it doesn't matter whether you take wired or free boundary conditions. You'll get the same local picture near the origin. Okay, so what I'd like to do now is use this fact from percolation to prove the Chayes and Newman, Chayes squared and Newman result. So let's go straight to that. So I want to show this by, so my goal will be to fix arbitrary lattice points UV, okay, and just show that the invasion percolation, I've started calling them invasion percolation trees, the trees built by Prim's algorithm. So the invasion percolation trees, TU and TV, almost surely intersect. Okay, if that's true for any pair of trees, then that means that all of these trees join up into one big tree together, right? So this, so if we prove that, we prove the theorem. And in fact, we'll prove slightly more than this. We'll actually show that for any two vertices of the lattice, the invasion percolation trees will almost surely only differ on a finite number of edges. So their symmetric difference will be finite. Okay. So to prove this, we're going to find one of these open loops that we said was guaranteed to exist, which surrounds U and V to start. Okay. So let's let n be large enough that U and V are in minus NN, and then let gamma be an open circuit of the critical percolated lattice, which doesn't intersect that box. Okay. And one more, I'll draw a picture in just a second, but let me give myself one more definition. Let's let C gamma. So these edges are all open, right? And so now there might be other, so this is some circuit of open edges, but there might be other open edges connected to that circuit, sort of going here and there and everywhere. Okay, and those form a connected component of this percolated lattice. So I'll call that C gamma. So that's the connected component of Z2½ containing gamma. And so now let me grab my picture of that. Okay, so here's here are U and V. In yellow we have the box minus NN squared, right? And then in red we have the circuit gamma, and then so the red plus the black is C gamma. So everything, you know, the circuit plus everything attached to it by open edges. Okay, so yeah, you know, maybe black should have been blue for my previous conventions, but I hope the picture is clear. This is a connected component with all edge weights less than 1/2. So I've taken an open circuit here rather than a closed circuit. There was a question in the chat whether these are edge weights greater than or less than 1/2. Yeah, so let me say, so that's important. So all red and black edge weights are less than 1/2. Okay. And now let me give myself one more definition and a new color to go with it. So let's let E gamma be the set of lattice edges in the unbounded connected component of R2 when this component C gamma is removed. Okay, so maybe I'll make my picture a little bit more, just a very slightly more involved by adding one edge. Okay. So then the edges I'm talking about are sort of all of these edges out here. Okay, every edge that when you remove everything inside this this region spanned by C gamma, what heads to the rest of the world? Z2 minus. So I think what I'm saying is, if you remove all of these, if you view these edges as embedded, right, then you remove all of the vertices and edges of the component, then you're left with an unbounded. You're left with a bunch of connected components of R2 of the plane, and one of them is unbounded. Yeah, and that component is unique because C gamma is almost surely finite. So this is C gamma is finite almost surely, since there's well, all components of Z2 at the critical percolation probability are finite almost surely. So there's this unique unbounded component. Okay, is that picture clear enough? So now let's think about what Prim's algorithm or invasion percolation started from U and V are going to do. Okay, so at the start they each do their own thing. You know, U explores over here, V explores over here. One of them might hit C gamma before exiting this box. One of them might exit the box first and then hit C gamma. Okay, but all of the edges at the moment that, say, the exploration from V enters C gamma, right? It did so by following an edge of weight at least a half, because C gamma is a component of the graph where the edges have weight at most a half. The whole boundary of C gamma has weight bigger than a half, right? So all edges leaving C gamma have weight greater than a half. So that means, you know, the exploration from V, it goes along somewhere using maybe some edges of weight bigger than a half, some less than a half. At some point it adds an edge into C gamma, and at that point all the edges leaving this bounded region that it's explored have weight bigger than a half. Okay. And now it can, you know, do some nice long exploration inside of this component using only edges of weight less than a half. Right? And similarly, starting from U, you know, the exploration goes along. At some point it adds an edge into C gamma. That's forced because it's trapped in a bounded component, so it certainly eventually has to touch C gamma. Okay, and then it can do some nice long exploration within C gamma. Okay. There's a question in the chat, shouldn't be bigger than, or equal than a half. The edges that connect to C gamma are not in C gamma, so they must have weight at least a half, because C gamma has only edges of weight. C gamma is a component of the graph with edges of weight less than a half. Okay. There's another question in the chat. Is this closed circuit part of the original graph or in the dual? This is, so all of the red and black edges have weights less than a half. So that means they're open edges, if you like. Okay, but I mean, if the point is that the invasion percolation likes small weight edges, right? So it's gonna, once it gets into this component, it's gonna be happy for a while. It's gonna explore within the component until it is forced to leave. Another question in the chat. If it would be in the original graph, then there could be an outgoing edge of gamma that has smaller weight. I'm not sure I understand the question. I'm sorry. Right. So we took a circuit, all of whose edges had weight less than a half. We took its connected component, and then this is the sort of, well, not just the outer edge boundary, but in particular includes the outer edge boundary. Okay. So now the point is that you know, when either of these two explorations decides that it's done as much as it can within C gamma and has to leave for the unbounded region, okay, it's going to take the smallest weight edge in the unbounded region. Okay, it's going to take the smallest, it's going to follow the smallest green edge. Because, I mean, it always follows the smallest available edge. And so in particular, when it has to choose an edge of E gamma, it'll choose the smallest edge of the unbounded outer boundary. Okay, and so that's true for whether the exploration starts from U or from V. Okay, so Prim's algorithm started from either U or V, explores the same subset of E gamma, and in the same order. Right? Because because for as long as the exploration chooses not to explore in the well, for as long as the exploration has edges of weight less than a half available to it, it will explore them. And when it ceases to have such edges available to it, well, you know, the first thing it might do is do some more exploration on the inside of the component. The smallest available edge of weight greater than a half doesn't have to lie in the unbounded region. Okay. But when the algorithm is, wherever it starts, when the algorithm is forced to explore into the unbounded region, it'll take the smallest weight edge leaving for the unbounded region. Okay, because it will already have had to fully, you know, to touch every vertex of CV, because all those vertices can be reached by edges of weight less than gamma. Okay, and then so you know the first, whether you start from U or V, the first edge of E gamma you explore, you know, will be the same. Maybe it's this edge here. Okay, and then after that, the second edge of E gamma you explore will also have to be the same, because the first one was the same, and so now you again have the same sort of outer edge boundary. Maybe the second edge you explore is, you know, over here, or maybe it's one that attaches to the first edge. But whatever it is, at each step of the algorithm which does explore into the unbounded region, the set of available edges is paired up so that those are always the same outer boundaries. And so the exploration has to always choose the same next edge, because it's always that one edge that is the smallest weight edge that remains. Okay, so that means so in particular that if we look at the subtree of TU that intersects E gamma, that's the same, not the size, but the actual the collection of edges of TU in E gamma. That's the same as the collection of edges of TV in E gamma. Okay, and so that means that, well, in particular, the intersection of TU and TV is non-empty. You know, they're infinite trees, and all but finitely many of their edges have to be in E gamma, because the rest, the part of the graph that's not in E gamma is just some bounded region. Okay, so this is non-empty, and more strongly, the symmetric difference of these two trees is finite. Okay, so that proves that that the minimum spanning forest in this setting is in fact a tree. And there's a question in the chat: does this make the minimum spanning forest a one-ended tree? Indeed. So the minimum spanning forest is one-ended, right? And so that means that you know, for any two paths, so for any two infinite paths, gamma and gamma prime in the minimum spanning forest, almost surely the symmetric difference of the paths is finite as well. Okay, so so there's really only one way to go to infinity, if you like. Okay, so are there any questions about that part of the proof, or that proof? I'd like to talk a little bit more about the two-dimensional case still. I'm going to talk about scaling limit results. So here I won't be telling you proofs, but I'd like to tell you some of what's known, and also leave you with some open problems in the planar setting, because there are definitely interesting things left to do before we move to the mean field setting. Okay, so we're now going to talk about scaling limits in Z2, and this is really, I guess I'll call it, whoops, the Garbin-Peter-Schramm theorem. I mean, that set of authors, in fact, had more than one theorem, but I see there's a question, so before I go on to that. The minimum spanning forest is one-ended. Right, so so if you think about what this says, it actually says that if you well, let me try to explain. Maybe I can try to explain why it's one-ended in a little more detail on the break. I'd like to just finish with the planar percolation discussion first. Yeah, I also need a second to think about that. And I think I missed an M. Okay, so so the setting for this discussion is the triangular lattice. Okay, so this is not a sort of fully universal picture, because we know more about planar percolation for certain special lattices than for other lattices. So I'll write T for the bold T for the triangular lattice. Okay, and in fact, it's not just for the triangular lattice; it's for a sort of special way of constructing the edge weights, because it's really the setting, the percolation setting where we know the most is for site percolation on the triangular lattice, and the proof actually exploits that structure. And so, in order to get the most detailed understanding of scaling limits, you need to tailor your minimum spanning tree setting to agree with where the most is known about percolation. So these authors look at vertex weighted. They build a vertex weighted MST. So you start with a collection of weights on the vertices of the torus, which are IID uniform, say, and then define edge vectors. So for an edge UV, the edge vector is so the maximum of XU and XV, and then the second coordinate is the minimum of XU and XV. Okay, and then they use these vectors to build the minimum spanning tree, or let me call it a minimum spanning forest, even though it is indeed a tree. So the rule is that, so if you like, you can think of our regular idea of increasing, of sort of having a parameterized family and adding an edge when it arrives, if it joins distinct connected components. Okay, but now the ordering will take us the lexicographic ordering with respect to these vectors. Okay, so that means that an edge UV is in the minimum spanning forest if U and V are in different connective components of, let me call these the entries of this vector W1UV and W2UV. So different connected components of the subgraph of the lattice that you get if you only keep edges that sort of lexicographically precede this one. So that's T W1UV, W2UV minus. Okay, so that feels a little bit clunky. It's a sort of precise way to define the minimum spanning forest, but there's a sort of maybe a nicer way to think about what this process is doing in terms of activation times for the vertices. Okay, so if you think of vertex V activating at time V, then you can rephrase this this discussion as follows. So, or this definition as follows. So when a vertex U activates, so that's going to be at time xu, then it'll try to add edges to its neighbors. So it can only add edges to its active neighbors, okay? So to its active neighbors in increasing order of their weights. Okay, that's an equivalent description, right? Because the first coordinate says that when a vertex, you know, when we start to try to add edges from a given vertex to neighbors, to a neighbor, it has to have the bigger weight. So, you know, if U has a smaller weight, then it doesn't get to try to add this edge because V hasn't been activated yet. V has the bigger weight, V will be the one to try to add this edge. And then, so when V activates, it looks at all of its active neighbors and tries to add the edges one at a time. Okay, so an edge is added if and only if it doesn't create a cycle. Okay, so is the definition clear? So you order the edge weights lexicographically for the purpose of Prim's algorithm. That was a question in the chat. Well, I mean, it isn't really for Prim's algorithm. What I've described is really closer to Kruskal's algorithm, I think, because it's sort of a global definition. It's, if you like, it yields a dynamics which is sort of very reasonably natural, fairly equivalent to Kruskal, and is closely enough coupled to site percolation for the tools of site percolation to be available. I don't know if I have a more detailed justification for it than that, or it's just a formalization of this story using the lexicographic ordering, if you like. Okay, so so the theorem that's proved by these three authors is the following. So we're going to rescale the lattice. So we'll let Tn be the triangular lattice, but of mesh size 1 over n instead of 1. And I'll let you know, MSTN be its minimum spanning forest. Okay, then, so informally, this minimum spanning tree converges in distribution. Okay, and to be a little bit more formal, you know, it takes, making sense of this requires me to tell you sort of what I mean by convergence and distribution in this context. How you know, and that requires a bit of thought, because these are objects that span, you know, as the mesh size gets small, they're spanning a dense set of points in the plane. So, you know, if you just naively zoom out and think about the, you know, say the Hausdorff sense of convergence for this subset of the lattice, you'd just be converging to the whole plane. Okay, so if you do something too naive, there's sort of no hope for a non-trivial limit. But you know, what you really want to, well, one natural thing to try to understand is what the curves within this minimum spanning tree look like if you take two you know, points that are macroscopically separated and ask what the shape of the random curve in the minimum spanning tree is that connects them. And their theorem addresses that sort of question. So being a little bit more formal, so in particular, you know, if I fix some number k of points in R2, and then I fix a sequence of lattice points that converge to those points. So xn1 up to xnk and Tn such that, so xni converges to xi for all I from 1 to k, okay, then the subtree, so let me write MSF n of xn1 up to xnk, right? So this is, so we have some minimum spanning forest on this lattice of mesh size 1 over n. It's almost surely a tree. So I can look at the subtree of that tree spanned by a collection of points. That's just the union of all of the paths in the tree between those points. That gives me some random tree embedded in the lattice. So it's some random closed subset of the lattice, okay? And that tree converges. So, so that subset of the lattice converges in distribution with respect to the Hausdorff distance. On closed subsets of R2. Okay, so that's so that says that there's some sort of you know, consistency in these pictures as the mesh size gets small. So let me show you a picture of what the limit looks like. So we saw part of this picture before. We saw this, okay. But what this theorem is telling you about is about, you know, if I fix, you know, some collection of points in here and ask about what's the shape of the tree that joins up these points within this minimum spanning tree, there's a description of that. So this is the sort of picture that you get. Okay, so you have these some sort of fractal paths connecting points. Okay, and this picture is a little bit of a lie because the endpoints here are not actually uniform points in this picture. This is a bit of a special spanning tree. So the edges that I've highlighted in this picture, the edges that are in black, so the whole picture has 100,000 points, and the edges that are highlighted in this picture are the edges that have at least 5,000 points on either side. So they're the sort of highway edges of the tree. They're the edges that have at least 5% of the tree on each side of the edge. Okay, so if you pick a typical point, it's probably going to be, you know, often one of the little like clusters of points hanging off of the ends or hanging off of the sides of one of these points somewhere. Okay, but this is sort of giving you a relatively good description of the global structure, and what you'd expect if you sort of sampled 2 random points now is that the path between them would look like first some little initial segment to hook you into the highways, and then follow the highway, you know, and then leave the highway, take the byroads to the point on the other side. Okay, so that's, I mean, yeah, so this picture isn't a perfect illustration of their theorem, but it does give you some idea of the sorts of random curves that their theorem is about. And in fact, their theorem kind of talks, an aspect of what they prove talks about the kind of important parts of the road network as well. I'd like to state that. So this is one property of the limit that they derive, which you can think of as a statement precisely about the black roads in that picture. So, in the limiting tree, so let me call that T infinity. And by the limiting tree, you know, there's some work that needs to be done to make this formal. It's the same work that's required in understanding what it means by convergence and distribution. But if you like, in these limiting curves, in this collection of limiting curves, you could say, so the dimension of the curve connecting any 2 points is bounded away from 1 and away from 2. So it's, you know, it's at least 1 because it's the image of a line, and it's at most 2 because it lives in 2-dimensional space. But in fact, it's strictly bounded away from those. That fact was actually known due to earlier work by Eisenman Burchard, Newman, and Wilson. Okay, and then the thing that I sort of said I was about to tell you is about the black curves. So this says that the dimension of the curve connecting any two branch points of T infinity is almost surely bounded above by, well, is strictly less than 7/4. Okay. So, so this statement, what this statement says is precisely that if you stay away from the most insignificant little rural roads of the tree, if you move inwards to after there's been some non-trivial branching, so that there's sort of some macroscopic mass, then the curves, then there's an upper this upper dimension bound on these curves that's 7/4. Okay, so you might think, well, if this, so this result is saying something like, as soon as you move away from the leaves of this tree, then the dimension of the curves is at most 7/4. And you might think that that implies that the curves themselves have dimension at most 7/4, but of course, you know, I can draw a sort of a curve that's smooth in the middle and then gets wigglier and wigglier as it approaches its endpoints, so that if I sort of move any positive distance away from the endpoints, I have a nice, smooth, rectifiable curve. But if I include the endpoints, then I don't anymore. Okay, so it's plausible that something like that is happening here as well. It's not ruled out by the result I just told you. Okay, so I'm going to finish this section on planar probability with some questions that remain. Two of them about minimum spanning trees, and one a kind of witness of the difficulty of studying distances and planar graphs. So the first one is about the going beyond this two-dimensional lattice setting, where you can, I mean, beyond the triangular lattice setting, where you can exploit a lot of special information about site percolation on that lattice. So let's look at the distance so the graph distance from 0 to the boundary of the box in the minimum spanning tree of Z2. Okay, so it would be nice to know, you know, this distance is trivially at least n, right? Because already, just if you want to, you can follow a shortest lattice path I mean, any path in the lattice has at least n edges to get you from the origin to the outside of the box. Okay, and it's also trivially at most like n squared, because the path can't do more than use like all the edges of the box. Okay, and so the conjecture is effectively just that neither of those bounds is tight. Okay, so prove that there's some positive epsilon such that dn over n to the 1 plus epsilon tends to infinity in probability, and dn over n to the 2 minus epsilon tends to 0 in probability. Okay, so there's I mentioned this result of Eisenman, Burchard, Newman, and Wilson before. So this is a result which more or less says that in the planar setting, you can use the percolation theory, in particular Russo-Seymour-Welch theory, to kind of get a toolkit for proving dimension upper bounds and lower bounds on the scaling limits of curves in random trees. So they managed to prove that for any subsequential limit of of these curves, the dimension will be strictly between 1 and 2. But their theorem hasn't, I mean, the way it's written, it doesn't actually yield concrete information about what happens for finite n. So it'd be interesting to know what's going on for finite n there. Okay, a second question is about a percolation setting which has seen some success recently, but for which much less is known than the planar setting still. So this is, I'm going to again look at the distance from 0 to sort of the boundary of some box. But now I'm including this cross K here because the lattice that we're interested in is a sort of fattened Z2. So you look at the lattice Z2 cross the integers 1 up to K. Okay, so think of this as just taking K copies of Z2 and then adding vertical edges between, level 1 and level 2, and then level 2 and level 3, and so on. Okay, so this graph is called, the slab. So in the last sort of 5 years, 6 years, people have figured out enough of how to extend enough of the percolation theory from the planar setting to this slightly fattened planar setting to do things like prove that there's no percolation at criticality on this lattice. Okay, and actually there's even one paper on the minimum spanning forest for this lattice, which shows that it's almost surely one-ended. Okay, so we know a little bit about the minimum spanning forest, but we don't know anything about its diameter. So in this setting, just proving that there's no Eisenman-Burchard theory either. So proving that the distance dnk, is superlinear would already be non-trivial, or proving that it's subquadratic. Neither of those facts are known. So really just the first non-trivial bounds. Okay. And, to give you just a sense of the fact that, understanding things, as I said, about graph distances in random subsets of the lattice can be hard. Here's a question of Chris Birdsey, which isn't directly about minimum spanning trees at all, but it's about random walks. So if you let Rn be the random walk trace, from 0 to the boundary of the box. Okay, so what does this mean? You fix a large box, you let simple random walk run until it reaches the boundary of the box. And this gives you some subgraph of, it could be a more complicated drawing, it could do all sorts of things, intersect itself a bunch, right? Then you look at, this thing is some subgraph of the lattice, and then let dn here be the distance from the origin to this boundary vertex. So in the graph Rn, so that's this guy in pink, okay? So prove or disprove that, there's some positive epsilon such that this dn is at least n to the 1 plus epsilon with high probability. Okay, so question is, does a random walk build you a quite direct route to the boundary of the box, or does it force you to take some circuitous route to reach the boundary? Okay, now in this picture, you don't have to follow the trajectory that the random walk took. You're allowed to take the most direct path that you want to get to the boundary. Okay, so that section took me a little bit longer than I expected, but that's it for planar minimum spanning trees and Euclidean minimum spanning trees, unless there are further questions. I'm going to postpone responding to the question about the one-endedness until the end of the lecture, just because I need to, I think if I try to do it online, I'm going to confuse myself. I'd rather sort of take 2 minutes to think before I answer. There's another question in the chat. Is this conjecture to be some kind of branching SLE? No, I don't think it is. I mean, in fact, the paper by, so these scaling limit, these pictures, there's a conjecture in the paper by Garban-Petersham about this, which is that the limit is not in fact a conformally invariant object. So it certainly has some sort of close links to critical percolation, but the curves are not exactly percolation curves. I mean, if you know, in particular, if you sort of take a given percolation component, it'll have lots of, at criticality, it'll have lots of small cycles all over the place. Okay, and then the minimum spanning tree operation will break those cycles in some way that relates to the edge weights. And there's a heuristic that they give for why that should not yield a conformally invariant object. Right. There's another question in the chat. Can you just talk a little bit more about the algorithm, please? I feel I didn't get the Garban result very well. So, so I guess the main, you know, this is the most detailed explicit statement I made about what they prove, is that if you take a sequence of lattice points which are converging to points in R2 and look at the random curves in the minimum spanning forest between those points, that gives you some, you know, random closed subset of R2. And if you like, you can couple those. So the convergence in distribution in the Hausdorff sense is equivalent to saying you can couple those trees as n changes so that those curves converge almost surely to some limiting curves in the Hausdorff sense. So that the, you know, if you just take this limit, you know, if you imagine that this is the limiting picture, okay, or this is sort of a guess for the limiting picture. If you just fatten these curves by, you know, giving yourself a little epsilon ball around the curves, then the finite trees can be coupled so that almost surely for all n sufficiently large, the finite trees stay within these fattened regions around the limiting curves. Okay, and maybe we can discuss a little bit more at the end of the lecture, if you like. Okay, so there's, you know, there are several beautiful results in the Euclidean setting. There's a lot that's left to prove. I forgot one more conjecture that I wanted to mention. This is in D greater than 2. So I mentioned that it's not known whether the minimum spanning forest is a tree in high dimensions, but in fact, there's an even weaker conjecture, which is that, so for any d greater than 1, the probability that the number of connected components of the minimum spanning forest in ZD is either 1 or infinity, that this should be equal to 1. So this isn't saying, you know, this isn't saying it's certain to be a forest. It's just saying it's either going to be a forest or it's going to be a tree. It's not going to sort of sometimes be one and sometimes be the other. There should be some sort of a 0-1 law or an almost sure result about the number. And this is saying it should be. Sorry, what I just said was a little bit accurate. Was a little bit inaccurate. This is just asking to rule out the possibility that there's some positive but finite number of connected components that's greater than 1. Okay, so that somehow should be much easier than determining that there are indeed infinitely many components, but we also don't know the answer to that. Okay, so that really is the last thing I'll say about Euclidean MSTs. And now we'll go on to the mean field. Let me take a 2-minute break and get some water. Okay, so continuing on. So the setting here is the complete graph with IID edge weights as before. Okay, and I'll write MSTN for the minimum spanning tree of KN with these edge weights. Okay, and I'd like to also give myself the general terminology. So diameter, so diam G is the maximum graph distance between any two vertices of graph G. Okay, so the goal of this section is to tell you about the diameter of this minimum spanning tree. So this is n to the third in probability. Okay, so so this is, if you like, this is a natural kind of question to ask in the same flavor of the questions one asks in the Euclidean setting. So in the Euclidean setting, you might want to know the dimension of these curves, right? But the dimension of the curves is sort of linked to the distance between points, because heuristically, if, well, you know, heuristically, if in the limit this curve has dimension 8/5, then that suggests that in the finite dimensional, in the finite lattice, you'd expect the sort of distance between 2 points to be like n to the 8/5, roughly. Okay, so you know, and similarly, you can sort of invert that and say if the curves, if sort of typical distances are of order, you know, n to the gamma, then the volume growth around a given point should be like n to the 2/gamma in order to sort of fill up the whole lattice, the n squared points by the time you get out to distance n to the gamma. Okay, so in the in a non-spatial setting like the complete graph, we can't necessarily talk about dimensions of curves, but we can still ask about volume growth and diameter, and that should in turn give us information sort of about how we might rescale the minimum spanning tree if we wanted to get some compact limit object. Okay, so this is a sort of natural first step to understanding the global structure of the minimum spanning tree. Okay, I'll also talk about the local structure later, and discuss how so this minimum spanning tree has locally cubic volume growth. Okay, so this is to say that if you look at, you know, the ball in the set of points in Kn, such that the distance from, say, 1 to V is at most R in the minimum spanning tree, that grows in some sense like R cubed. So there's sort of cubically many points at distance at a given distance from a fixed point. Okay. So these two facts are sort of clearly related to one another. So I'll tell you this. So there's a question in the chat. Do you want diameter minimum spanning tree? Yes, thank you. That should be the diameter of the minimum spanning tree. And the other question was, should this be for R fixed as n tends to infinity? Yeah, so in fact, we'll sort of talk about this directly on a kind of local limit object. that it is for r fixed as n tends to infinity, but you can also interpret it directly at n equals infinity if you like. Okay, so so let me start by giving you sort of the approach one can take to understand this diameter. So so remember that in Kruskal's algorithm, we coupled the minimum spanning tree growth with the graph process so that at all times the components are the same, right? So if I write FNP for the subgraph of the MST, of MSTN with only edges of weight at most P, right? Then we saw so the analysis of Kruskal's algorithm showed that you know, for any P between 0 and 1, GNP and FNP have the same connected components. Right? So let's think about what that means, what we can sort of instantly say about the structure of the minimum spanning tree, right? The minimum spanning tree in this language is FN1, right? It's what you get once you've added all of the edges, right? So I want to think about what our information about the component structure of the Erdős-Renyi random graph then tells us about the structure of the minimum spanning forest, right? And I'm going to focus on the regime where we know that the kind of macroscopic structure of the macroscopic components emerge in the Erdős-Renyi process, right? So when C is less than 1, there are no macroscopic components. We saw that all components are logarithmic in size. Right? Whereas when C is bigger than 1, there's a unique component of linear size. And then all other components are logarithmic. Right? And then for C around 1, we worked quite a bit to understand the typical structure or the sizes of the largest components in the Erdős-Renyi process. But focusing on what it means for the forest now, just already at this level of granularity, we see that, you know, here there's already a unique component of linear size in the tree, or sorry, in the tree process or the graph process. Okay, so that means effectively the large scale structure of the minimum spanning tree is already formed. Everything that happens after that will be just the attachment of little pieces to a global skeleton that's already present. Okay, so this is really the point when the large scale structure of the minimum spanning tree forms. Okay, so so we're really going to understand the diameter by zooming in on what happens around C equals 1 in the Erdős-Renyi process. Okay, so so to estimate this diameter, we'll zoom in near C equals 1. So we'll be looking at so FNP for P 1 plus epsilon over n, and epsilon sort of little o of 1. Okay, so this won't be nearly as technically challenging as when we studied the Erdős-Renyi graph. We'll use some of the results we got from studying the Erdős-Renyi process in this range, but we won't have to do any sort of detailed analysis like we did there. So let me start by just seeing how this connection can be exploited to get a lower bound. The lower bound in this theorem is quite straightforward. I can basically prove it to you right now. So I'd like to do that, and it'll give us a sense of how more generally we're going to use the connection. Thanks. Comment in the chat that should be 1 plus epsilon over n, on the principle that probabilities should stay less than 1. So I'm going to show you that. So this is the lower. Let me say this is the diameter lower bound. So for any positive delta, we can find a k such that the probability that the diameter is less than n to the third over k is less than delta. Okay, so that says that the diameter is at least n to the third of order n to the third in probability. Okay, and let's we'll prove this just by looking at what happens for epsilon is 0. Okay, so let's let h be the largest. Well, I'll say C max of G and 1 over n. Okay, and I'll let T be its minimum spanning tree. So T is the component of Fn 1 over n with the same vertex set as H. Okay, so you know, here's the component, right? So this is H, and its minimum spanning tree is something that looks like H but doesn't have cycles. So maybe it's that, right? So I've sort of broken cycles there and there. Okay. Well, breaking cycles can only increase the diameter, right? So when I remove an edge, this minimum spanning tree is obtained from H by removing some edges. That can only make the diameter increase, right? So the diameter of minimum spanning tree, well, this tree T is contained in the minimum spanning tree, so that diameter is at least the diameter of T, which is in turn at least the diameter of H. Okay. But now, you know, when we were studying the critical random graph, we saw that the size of the largest component in this regime is order n to the 2/3, right? And its surplus is order 1, both in probability, right? And so that means, I mean, just making these statements quantitative, that says that we can choose some A such that the probability that, you know, H has size at least n to the 2/3 over A, and the surplus of H is at most A, is bigger than, say, 1 minus delta over 2. Okay, so we're just saying that the probability that H has size at least a small constant n to the 2/3, and the surplus is at most a large constant is large. Okay, but now, you know, what's the structure of H, right? Conditionally, given the size of H is M and the surplus of H is S, then, you know, H looks like a uniformly random element of G, so a uniformly random graph with M vertices and surplus S. Okay, this is a slight lie, because the vertex set of H isn't 1 up to m like over here. But if we relabel the vertices of H in increasing order so that the labels are just 1, 2 up to m, then this is literally true, right? And we saw that, you know, what does a graph like this look like? It has sort of path lengths of order m to the half in its kernel, right? And then onto those path lengths, onto that core that's built from the kernel by attaching these random lengths, then you attach, you start this line breaking construction, right? So you have some, this is the sort of schematic of a graph H with large size. So this is where m is large and S is bounded. First, you picked some random 3 regular graph, some according to some probability of seeing given kernels, right? So some picture like this maybe, right? And these edges, these path lengths were all of order square root m, and then onto that you started attaching sticks according to whose lengths are distributed according to an inhomogeneous Poisson process. Okay, so so this is you know, path lengths in the core are of order m to the half in probability in particular, right? So that says that, so here we have a graph which with high probability has size of order n to the 2/3 and bounded surplus, okay? So that means that the path lengths in the core of that graph will have length of order, well, square root of this with high probability. So, you know, that means there's some, well, let me say that for any A like we saw above, we can find some other constant B such that if the surplus is at most B, then for a graph which is uniformly drawn from GMS, the probability that the diameter is at least, so square root of size divided by B is bigger than delta over 2. Okay, so that means that first with high probability, we have a large graph, this large, with surplus at most A. And then if that happens, then with probability, with high probability, sorry, that should say the probability of the diameter is less than, that is less than delta over 2. Okay, then with high probability, the diameter is at least of order square root of the size. Okay, and so that says that, you know, combining those bounds gives that the probability of the diameter is at least, so n to the 2/3 over A. That happens with high probability from the first bound, and then we take, that's our m to the half over B. That happens with high probability from the second bound, that's at least 1 minus delta. Okay, and so that's what we were aiming for. The diameter of H should be of order n to the 3rd, right? And here we have a lower bound, which is of order n to the 3rd. Okay, so that's so that just says already by looking at what happens in the random graph at the critical probability 1 over n, and just focusing on the largest component, we already see a diameter lower bound for the minimum spanning tree of the order we claim. Okay, and so that in some sense means that we're very close already at the critical probability to building the whole structure of the minimum spanning tree, right? The diameter is the global structure. I mean, the diameter is already n to the 3rd, and we're claiming in the theorem that it's going to stay n to the 1/3 even if after we glue all of the rest of the bits of the forest onto this one component. Okay, so the challenge now is to understand why when you increase this probability from 1 over n and all the other trees in the forest start to attach themselves to this largest component, that it doesn't cause the diameter to shoot up. Okay, and well, roughly the reason for that is because this component will quickly sort of become this unique giant component, and all of the other components quickly become small. So when they attach on, their contributions become more and more insignificant. Okay, so it's not clear at that level of discussion that should be that should yield like a summable bound. There's some work to do to see that it really does. But that's the heuristic story that we're going to develop more rigorously in the next lecture. Okay, I'm wondering if there's anything anything else I can say today. Maybe I'll just leave you with one exercise, which I'll use in the next lecture. So when we used this picture here to get a lower bound, all I did was to say, well, if there's a long path between two vertices in the core, then that means that the diameter as a whole must be large, or equivalent. Or you could even just say the length of the first stick that attaches to this core was already of length sort of order square root m. So that gives us a lower bound on the diameter. Okay, but if I want an upper bound, even at this critical just an upper bound on the diameter for this picture, then I need to account for how much the diameter increases when I remove edges, right? And you should think if I only have to remove a bounded number of edges, then the diameter shouldn't increase very much. Of course, if I remove an edge that splits the graph in two, then I've just increased the diameter to infinity in a sense. So you have to be a bit careful. But the exercise is just asking you to work out what happens when you remove an edge that doesn't disconnect the graph. Okay, so here's an exercise I'll leave you with. So so for any graph G and any so vertices UV, then the diameter of the graph that I get from, I'm phrasing it in terms of adding the edge. So the diameter of G plus UV is at least the diameter of G minus 1 over 2. Okay, phrasing it in terms of adding an edge means I don't have to worry about whether or not the removal disconnects the graph. So this just says adding an edge can't cause the diameter to go down by more than a factor 2. Okay, so that's a good spot to leave off for today. I think tomorrow we'll prove the upper bound of that matches this lower bound. And if that doesn't take us to the end of the day, though I think it will, then I'll gently start to talk about the local structure of the minimum spanning tree. Thanks, everybody.